Right then, who's ready to do some radical solving index equations? We all are. Right, first, let's get sorted with the... Brilliant. So then, you'll find there's a sheet which Mr. Mackenzie has found, which has got some fantastic questions on it, all about the index work. And the first one I'm going to look at is similar to these ones. It's an algebraic one. It's probably unfamiliar style of question. So I've done it with a base of 7. What do I mean by that? So let's, for instance, say that we're told that x is 7 to the m. We don't know what m is. We don't need to know what m is. This is all about writing things in terms of the other. And let's say that y is 7 to the n. I think the questions on the sheet have a base of 3 or 5, but the principle's the same here. How could we rewrite 7 to the n plus 3 in terms of x or y? The thing to remember is if you've got addition in the index, you've got multiplication of two things with the same base. That's this rule here, okay, one of the index rules. You need to know the rules in the red box before you do any of this. Okay, so we can write an index as m plus 3 as a multiplication of 7 to the m and 7 to the 3. The 7 to the m is x, 7 to the 3 is 7 to the 7 is 49, times 7 is 343. So 7 to the m plus 3 is 343x. That's supposed to be, say, m plus n there. 7 to the m plus n. If there's addition there, we can put multiplication there. X times y. If x is 7 to the m and y is 7 to the n. What would 7 to the 5n be? As well as the division rule, there's this rule that's saying if you have a product of things in the index, we could have got them by rewriting like this. The base raised to the power, raised to the power. So 7 to the 5n could be written as 7 to the n raised to the 5. Multiplication here is inside and outside a bracket there. Multiplication there is numbers arranged like that. And so 7 to the n is y. You see, I got myself confused. My x's and y's there originally. Y to the 5. What about something like 7 to the m over 3? Well, we can write the m and the third inside and outside the bracket because m over 3 is the product of m and a third. So you could just write that as x to the third, or if we like, we could remember that a fractional power is a root. That's going to be important later. So we could write it as the cube root of 7 to the m, the cube root of x. Both equally good. Now these are all good hard questions, okay? They're all killers and there are no fillers on this sheet. So prepare for your brain to be expanded. That's why I'm keeping my hat on so my skull doesn't crack. I'd advise you to do that. Wear a tight fitting hat for these questions. So there's quite a lot about change of base in some of the questions. So for example, if I take the power series for 3, we get these results and so on. That means if I want to write 27 to the 4 with 3 as the base or as an index of 3, rewrite the 27 as 3 cubed raised to the power 4 and the index rules from the previous sheet. And I think my starting point would be, once you've seen the video once, go back to the first sheet, get those index rules in front of you, because without those, we can't do these. 3 to the 4, 3 to the 12, 3 times 4. So 27 to the 4 is the same as 3 to 12. You could check that on your calculator, couldn't you? Type in them both, check you get the same answer. Could we write 81 to the y times 3 to the 5 in terms as of a single term raised to the power, So a single term of 3 to something. 81 is 3 to the 4 raised to the y. That becomes 4y. If it's multiplication there, we add the indices. It all comes back to the three rules and then the results after them. And we can extend that to solving equations with indices in them. The key is here the base on both sides is different. If you can write it so it's got the same base, we can equate the powers. So how do we do that? 27 is turned into 3 cubed. The rule for these indices inside and outside a bracket is multiply them. X must equal 6 because the base was the same, matching the base. How complicated can we make it? Well, it's Mr. Mackenzie's sheet. It can be super complicated. So I've got another example. It's not on the sheet. So 3 to the x is equal to 9, big 9. 3 cube rooted. If you don't write it clearly, you're going to mix what numbers are small numbers for the roots and big numbers for the coefficients. 9's 3 squared. The cube root of 3 is 3 to the third. Because we have multiplication, we can add them. 2 and a third, so x must be 2 and a third. I don't like mixed numbers. I'd write it as 7 over 3, so x is 7 over 3. But of course, 2 and a third, 7 over 3, absolutely the equivalent. It's just fashion, writing one, not the other. Right, don't read these until you've tried the questions, okay? So, pause it now, try the questions, come back. You're back? Here are some worked answers. So I think it's from, you'll see where it's from. So solving these equations, the key is getting the bases to match. And it's just inordinately complicated, but it's only one step at a time. That's the key here. It's the key to the rearranging. It's the key to this. It's key to so much. One step at a time, clearly expressed. Keep your faith with things. So 9 to the 4 is 3 to the power 8 because 9 is 3 squared. 3 squared to the power 4. 2 times 4, 8. 3 to the 8 cube rooted is 3 to the 8 over 3 because a cube root is a power third. 8 times a third is 8 over 3. This is a reciprocal. So we then introduce a negative power there. N is minus 8 over 3. Brilliant. So you might want to now try the next one before you read this next answer. Okay, so the next one. We have the simplest, the smallest number here is 3. 9 and 27 are both in the power series for 3. So that's the clue, all in terms of base of 3. 3 cubed to the quarter, because that's what a fourth root is as a power. Cube root is a third as a power. 9 is 3 squared. Multiply the 2 and 2 with the third, multiply the 3 with the quarter. Add them. I didn't have my calculator in reach, so I did it properly. 3 to the 1 over x is 17 over 12. So the 1 over x is 17 over 12. Lovely bit of rearranging. Brilliant, aren't they? So at this point, the next page is a couple more word solutions, but on Thursday, I'll send you all the work solution for the hardest ones. There's no expectation you get through the whole sheet of these, because I think this PowerPoint will take 12 minutes. But the further you get through, the better. These are incredibly good questions. Right, so the next one he's gone through is, can we find what the 2k plus 8 is? How do we do it? How do I know how to do it? The clue is we've got 3 and 4. I'm always thinking about prime numbers, okay? 4 is 2 squared. 24, well, suddenly as I'm thinking through it, but 24 is 8 times 3, which is 2 cubed times 3. How on earth does that help us? That 3 cancels with that 3. I've now got a problem with 2 cubed on one side and 4, which is 2 squared there. Multiply them. They must be the same. Solve it. I defy anybody to have seen at the beginning that the answer was that, because these questions, they're the overlap with the GCSE and the higher GCSE qualification, but they are all just the rules for indices. Okay, right. Oh, it was getting too big there, brain expanding too much. Can we write this? Can we write that y to the 5 quarters in standard form in terms of k? What a brilliantly bizarre question. Where on earth are we going to go with that? Well, first of all, y to the 5 quarters is this raised to the power 5 quarters. How on earth do we do that? Because that's a product, I can do each bit separately. Why 16? Because 16, if you go 2, 4, 8, 16, 2 to the 4 is 16, 16 to the quarter is 2. So, check it on your calculator. 16 to the 5 quarters is 32. But why? 2 to the 4 is 16, 16 to the quarter is 2, and 2 to the 5 is 32. 8 times 5 quarters is 10. That's not standard form, not even a sting in the tail. 32 is bigger than 10, so divide that by 10, which means we add 1 to the power there. Now, that's 12 minutes and 10 seconds now. You've hopefully watched this final bit with doing the sheet. I think there's enough to keep anybody going there for an hour. And also, there's a good number of you, a really good core of you, who keep saying, well, we don't mind the harder questions because we don't mind if we can or can't do them. We like thinking about them. And please remember, that's what this is about, thinking about harder ones. And I don't really care at this stage if we can do them without the help, because the teaching side is teaching how to do them. And this is what this sheet's about. Good luck.